Welcome to CS 1401 Video 20.2. In this video, we'll continue our exploration of programming in Prolog, looking at 4 more recursive algorithms for lists. First, let's look at a program for summing the numbers in a list. Remember that Prolog returns only true or false, so our Prolog predicate will instantiate one of its arguments that makes the predicate true when that argument is the sum of the numbers in the list. Not surprisingly, I've called this predicate sum. Let's take a look. The base case is when the list is empty. That is, if the list doesn't have any numbers in it, then the sum of the numbers must be 0. The recursive case is when there's at least one number in the list, and that number will match h. T matches the tail of the list, which could have multiple numbers in it, or it could be empty. The idea is to call sum recursively with the tail of the list, and that will calculate the sum of all the numbers in the tail of the list. Then the sum of the entire list is going to be that first number, the head of the list, plus the calculated sum of all the numbers in the tail of the list. Let's try it out. My first test case will be when the list is empty. I'm expecting that Prolog will unify x with 0, and that's exactly what happens. My next test case is when the list has exactly one element in it. So I'll try it out where the list has just the number 7 in it. And I expect that the sum of all the numbers in a list that has just 7 in it should be 7. And that's what Prolog tells us. Finally, I'll try out sum with a list that has multiple numbers in it, in this case the list 1, 2, 3. I expect that the Prolog interpreter will unify x with their sum, which is 6. And that's exactly what happens. Next, let's look at a Prolog program that builds a sublist of item in a list that meets a certain criterion. For example, we could write a program that, given a list of numbers, builds another list that contains only the positive numbers in the original list. Or, and this is what I'll implement, we could write a program that, given a list of letters of the alphabet, builds a list that contains only the vowels in the original list. For example, if the original list were S-O-O-N-E-R, then my result should be the list O-O-E. I've named my program vowels. The base case is when the list of letters is empty. In that case, the list of all the vowels will also be empty. There are 2 recursive cases. The first recursive case is when the first letter in the list, the head, is a vowel. I can check to see if it's a vowel by defining a set of predicates called val. So vowel of A will be true, vowel of E will be true, and so forth. So if the head of the list is a vowel, then I know that the head of the list I'm building will also be a vowel. What's the tail of the list I'm building? Well, that will be all the vowels in the tail of the original list. I get that by calling vowels of T, T2 recursively. The other recursive case is if the head of the list is not a vowel. So in that case, I can match the head with the underscore because we don't need it anymore. And I'll simply instantiate T2 to be all the vowels in the tail T. Let's try out our program. First, I'll check to see that it works with the empty list. I'm expecting here that the Prolog interpreter will unify L with the empty list also. And that's exactly what happens. Now let's try running it with a long list of letters. I expect that L will be instantiated to the vowels in that long list in order. Let's see if it works. Yep, those are the vowels, and they're in the right order. My program works. You can apply this technique to lots of similar problems. For example, you might try writing a program that, given a list of animals, builds a list with all the animals except sheep. Here's a similar program that builds a list of the odd numbers in a list. I'm calling the predicate for this program odds because it builds a list of the odd numbers in the original list. The base case is when the original list is empty. In that case, the list we're building of odd numbers should be empty too, because there are no odd numbers in an empty list. There are two recursive cases. The first recursive case is when the head of the list is an odd number. In this case, the head of the list we're building should be that odd number. What's the tail of that list? Well, the tail of that list will be all the odd numbers in the tail of the original list. So to determine if the head of the list is an odd number, I've defined a predicate called odd, and it returns true if n mod 2 is equal to 1. To find all the odd numbers in the tail of the list, I call odds recursively on the tail, and it builds a list called T2, which contains all the odd numbers in the tail. So the overall list I'm building will be H, the original head, followed by the tail T2 containing all the odd numbers in the tail T. The other recursive case is when the head of the list is not an odd number. In that case, we're not going to use the head of the list in the new list we're building, so that's why the underscore variable is there. Instead, we're going to instantiate T2 by calling odds on the tail of the list and instantiating T2 to the list of all the odd numbers in T. Let's try out our program. My first test case will be when the original list is the empty list. I'm expecting that L will be instantiated to the empty list too, because there are no odd numbers in the empty list. And that is correct. My next test case is when the list contains exactly one odd number, in this case 3. I'm expecting that L will be instantiated to a list containing just the number 3. And that works. Next, I'll test a similar case where the list contains a single even number. Now I'm expecting L to be instantiated to the empty list because there are no odd numbers in the original list. And that's right. Finally, I'll check the program on a longer list. In this case, I'm expecting L to be instantiated to the list 5, 7, 9. And the program works. The two programs we've just explored, vowels and odds, builds lists that contain selected items from a list. What if, instead, we want to have a list that has the same length as the original list, but replaces some of the elements? For example, we might have a list of letters, and we want to have an equivalent list where all the x's are replaced by y's. Or we might have a list containing both positive and negative numbers, and we want to have a list with their absolute values. Or, and this is what I'll implement, if we have a list of animals, we could replace each occurrence of sheep with goat. Let's take a look. I'm calling the predicate for my program swap animals. The base case is when the original list is empty. In that case, the list of all the animals with goat swapped for sheep should also be empty. There are two recursive cases. The first recursive case is when the head of the list is the atom sheep. In that case, the list I'm building should have in its place at the head of the list the atom goat. The tail of the list I'm building will be the tail of the original list with all the sheep replaced by goats. And I do that by calling swap animals with the tail of the original list and T2 as the list we're building for that tail. The second recursive case is when the head of the list is not a sheep. In that case, the head of the list we're building will be whatever animal is in the original head of the list, and the tail of the list we're building will be the tail of the original list with sheep swapped out for goat. And I can get that by, again, calling swap animals recursively on the tail of the list, building a list T2 with all the sheep replaced by goats. Let's try out my program. My first test case will be when the original list is empty, and I'm expecting to see the new list also be empty. Yes, that's right. Now let's try it when the original list contains a single sheep. I'm expecting L to be a list with one element in it, and that element should be a goat. Yes, that's right again. What if the original list has one animal in it, but that animal isn't a sheep? Well, I'm expecting to see L be that same list with that same single animal. And the Prolog interpreter instantiates L correctly. Finally, let's check swap animal with a longer list. Here I've got 2 sheep, and so I'm expecting L to be instantiated to the list dog, cat, goat, lion, goat, rhino. Let's try it out. And that's exactly what we get. The program works. So that's our exploration of programming in Prolog. When we programmed in Java, we implemented our algorithms in an imperative programming language. When we programmed in Prolog, we implemented our algorithms in a logic programming language. In most cases, the underlying algorithm was exactly the same, just the implementation differed across the 2 languages. We saw how one language, Java, seemed to be easier for implementing algorithms dealing with arithmetic, and one language, Prolog, seemed to be easier for implementing algorithms dealing with lists. And I suppose it should go without saying, Prolog is a lot easier to work with for algorithms that deal with logical reasoning. Usually, you'll want to choose a programming language that's appropriate for the kind of problem you're trying to solve. The kinds of problems that developers solve with computers and computer programming range from reasoning about questions for playing Jeopardy, to controlling passenger aircraft via an autopilot, to issuing payroll checks, to generating computer graphics for special effects in movies. These applications cover a lot of ground. So in the next videos, I'll be discussing the impact of computing. See you then.